Hi everyone, welcome to day 2 of week 3 of the Neuromatch Academy. Today we're going to learn how single neurons create network dynamics. My name is Juliana Georgieva and I am a research group leader at the Max Planck Institute for Brain Research in Frankfurt, Germany, and also an assistant professor for computational neuroscience at the Technical University of Munich in Germany. In my group, we aim to understand how organization and computation emerge in neural circuits, especially in the context of neural circuit development, where we investigate very early stages of postnatal development right after an animal is born. More generally, we're also interested in how synaptic plasticity shapes neural network dynamics during learning and behavior, building mechanistic models where we represent single neurons and synaptic connections that change via synaptic plasticity, in networks very similar to the ones that we will study today. We're also interested in more normative or top-down frameworks where we study how neuronal properties emerge from efficient coding principles such as information maximization. As you learned yesterday, single neurons can generate and represent information by using their combination of ion channels that operate on different time scales and complex morphologies. And we have known for a long time how to understand the computations that these neurons can actually achieve because of decades and decades of experiments that have enabled us to record these neurons at different portions of the dendritic tree and to understand how they process input into output. But as we know, many neural circuits in the brain are not made up of single neurons, but rather of interconnected populations of neurons with diverse properties and synaptic dynamics. Therefore, the lectures in this tutorial will cover how these single neurons can generate population or network dynamics. The roadmap for this day consists of 2 tutorials that are divided into studying rate models, namely network models whereby the activity of the neurons is described using firing rates. So we go a little bit away from the framework of describing single neurons by using their action potentials, and instead we describe the dynamics of these networks by focusing on the firing rate activity. That's why these models are known as rate models. The division into the 2 tutorials is mainly depending on how many populations of interconnected neurons we consider. So in the first tutorial, we will investigate networks of neurons comprised of a single population of neurons that have similar properties, for example, excitatory neurons that all code for the same stimulus feature. And we will use the mathematical framework of dynamical systems to understand concepts like AFI curves, fixed points under stability, and vector fields to understand how these networks generate dynamics and what this means. And in the second tutorial, we're going to expand the framework and introduce a second population, namely a population of inhibitory neurons that together with excitatory neurons generate interesting neural dynamics that we will study using the framework of 2-dimensional dynamical systems. And then we will define the notion of fixed points and their stability in this 2-dimensional system, as well as vector fields in a complementary way to the system with a single population. But first things first, let's begin by introducing our network models and defining several new concepts, such as the concept of an FI curve of the population and solutions for these equations that describe the activity of these networks. First, we will describe what we mean by a feedforward network. A feedforward network is comprised of 3 different ingredients. First, we have a layer of presynaptic neurons or inputs that we describe here by the vector U. We also have a single postsynaptic neuron. So this is a very simple feedforward network with a single postsynaptic neuron whose firing rate is described by the variable V. This is a scalar. And the way this postsynaptic neuron generates activity is by integrating the presynaptic inputs U weighted by some weight matrix M, which gives us the third component in the feedforward network, namely the strength of the synaptic weights or connection between the presynaptic inputs and the postsynaptic neuron. Now, to determine how this postsynaptic neuron generates a firing rate, we need to understand what the total input current is that this postsynaptic neuron that it receives from the presynaptic neurons. To do that, we assume that simply this postsynaptic neuron scales linearly the presynaptic input units, so that the total input current experienced by the postsynaptic neuron is just the product of each of the individual weights M sub j times the activity of the corresponding presynaptic unit U sub j. So then we can write a differential equation that tells us what the firing rate activity is of this postsynaptic unit V. We have a differential equation that consists of two parts. First, we have a leak term, so this minus V, that tells us upon the removal of a presynaptic input, how the activity of this postsynaptic neuron will decay in time. And this will happen not instantaneously, but with this time constant determined here by tau r. Similarly, there's a second part in this equation, namely f sub I, that tells us how this neuron can integrate the activity of the presynaptic neurons through this nonlinear function given here by f. So I denotes this current that it receives from the presynaptic units that can also be written as the dot product between the weight vector and the input vector u. So we can extend this feedforward network to include multiple postsynaptic neurons, V. So now V is a vector, not just a scalar. And we can write the very similar looking differential equation with a leak term and a driving term, where the input current from the presynaptic units weighted by the weights determines and drives the postsynaptic neurons in this vector V. Here, M is no longer a vector, but is a matrix. That determines, so each entry of this matrix determines what's the strength of the connection into a given postsynaptic neuron from a given presynaptic neuron. We can simplify this a little bit by taking this product, this matrix vector product, mu, and denoting it by a single vector I external. So I external is just now the product of the weight matrix and the input vector u. And we can simply replace that, and so now we get a slightly simpler looking equation. So this also allows us to simplify the schematic a little bit, where instead of this entire array of presynaptic units U that we had before, we now just have a single external vector I external input that goes into all of the postsynaptic units V. Again, we can simplify this even further. Instead of considering this entire postsynaptic array as effectively an array or a vector of firing rates of postsynaptic neurons, we can lump them together into a single population. So instead of having a vector of firing rates, we now have a single scalar which describes the firing rate of the entire population of neurons. And we can do this if we assume that all of these neurons have very similar properties that can be described by the same equation. So now we have an equation for the entire population described here by R that looks very similar to what we had for a single neuron earlier. So this is the framework that we will consider for the rest of the tutorial. So it's a description of the firing rate of the entire population in response to some external input, I external. To understand its dynamics, let's first see how this population responds after it receives some external input. So what does the population do? Does it grow? Does it decay in time after the input is removed? To do this, we look at its steady state by setting this derivative equal to 0, so where the activity no longer changes in time. And we get this steady state where the rate is given by the nonlinear function of the external input, with the nonlinearity given by this function f. This defines very naturally the concept of an Fi curve, namely R describes the firing rate of the population, and it tells us how this nonlinearity f tells us how the firing rate of the population depends on the total input current that it receives. This is known as an Fi curve because, for obvious reasons, f stands for firing rate, and I stands for input current, but in literature this is also known as the transfer function or the stimulus response function or even the tuning curve of the population. Here we have taken a sigmoidal tuning curve or sigmoidal FI curve described by this expression here, but depending on the system that you try to model, this can have a very different shape and might not even be monotonically increasing like the sigmoid that we have considered here. There are two properties of this FI curve that I like to point out that we will vary in this tutorial. And one is the threshold, which tells us how much input current is needed to drive the population to fire with a given firing rate. And the other one is the gain, which tells us how fast does the firing rate change as you change the input current. These two can be varied. So of course, we can increase the threshold. So this new FI curve in the dashed line here has a higher threshold, which means that you need more current to generate the same firing rate. Or equally, you can flatten the gain. So that means that this new FI curve with the dashed line indicates an FI curve where for the same change in the synaptic input current, you see a much slower change in the firing rate. We can, with this knowledge of feedforward networks and steady states described by the FI curve, we can visualize or we can numerically solve the activity of the population versus time. So you will have a chance to explore this in the notebook in a moment. So in this case, the population starts with the initial condition of 0.2 and it ends up getting to a steady state at around 0.9 as a function of time. This increase is not instantaneous, but is determined by the time constant of the population activity of the equation that we showed earlier. Okay, so in summary, what we have shown here is how to define feedforward networks that are purely driven by external input. And in the tutorial, you will have the opportunity to investigate the dynamics of these networks. These are describing the dynamics of a single population of neurons. You will have the chance to implement an FI curve and to investigate how its shape depends on the threshold and the gain. Then you will also simulate the activity as a function of time, and you will be able to determine how fast the activity converges to the steady state by varying some of the properties in the network.